It also does take longer for us to go through them and for me to teach through them than it does to actually do the problems themselves. Because most of the time with the problems we're going through discussing, I'm giving time for y'all to actually type it in. Remind me at the end of the hour, because I need a graphing calculator. I'd have to look and see. You have not. So, first one we're going to start off with is this one here. So it's the one immediately after the last one we did yesterday. And the first thing we can do is go on and graph this problem here. So we'll type it into the graphing calculator, 6x to the fourth minus 11x to the third minus 16x squared plus 2x plus 4. Then we can hit graph. Now this here, it's hard to tell at one of the spots, but does cross the x-axis 4 times. 2 of them are easier to see, and the other one that is very close to the x-axis does cross it, but it barely crosses it and goes back. Now, we can look at the table to see if any of these cross at nice points, but even from the graph, it does not look that way. And we do not have any y values that are 0. So what we have to do next is to find our rational zeros, plus or minus p over q, where p is the factors of the constant term, and our constant term in this case is 4. Which one of the factors of 4 are 1 and 4, and the other factors are? Well, 2 is. 2 times what is 4? 2. Now, even though 2 is technically repeated twice, we're only going to list it once. Because as we said yesterday, any factors that repeat, we're not going to write them twice. So all the factors that we would get from 2, we would also get from 2. So we don't need it twice. Factors of 6 are 6, 2, and 3. And now we're going to divide all the factors of p by each factor of q. Well, the first one we're going to divide 1, 2, and 4 by is 1. So we have plus or minus 1, plus or minus 2, and plus or minus 4. Because 1 divided by 1 is 1, 2 divided by 1 is 2, 4 divided by 1 is 4. Now we're going to divide each factor of p by 2. So we'd have 1 over 2 is 1/2. 2 divided by 2 is 1. We already have it. 4 divided by 2 is 2. It's already listed, so we don't have to list them again. Then we can move on to 3. 1 over 3 is plus or minus 1/3. 2 over 3 would be plus or minus 2/3. And 4 over 3 is plus or minus 4/3. And lastly, we're going to do the same thing with 6. So plus or minus 1 over 6 would be 1/6. 2 over 6 is 1/3. And 4 over 6 is 2/3. So these here are all the possible rational zeros. Questions on this so far? Well, as we looked at the table already, because we had plus or minus 1, positive negative 1 doesn't work. Because we can see that on the chart. Negative 1 gives us a y value of 3. 1 gives us a y value of negative 15. Neither one of those is 0. Same with positive negative 2 and positive negative 4. So we know already that 1, 2, and 4 positive negative cases are already gone. So those 3 possible rational zeros are out. Now it does leave us with the rest of them, rest of these here. And out of all these here, well, 4/3 is the only one bigger than positive 1 or negative 1. All the rest are between 0 and 1 or 0 and negative 1, yes? So if we look at the chart, well, not that, this, the graph, well, we do only have one value outside of negative 1 or 1, bigger than 1, yes? And it's actually between, well, that's 1, 2, 3. It's between 2 and 3, yes? Is 4/3 between 2 and 3? No, it's 1 1/3, yes? So there's a good chance 4/3 is not going to work. Now we can check that. So if y'all remember this here, second, calculate. Second, calculate. And if we select the first one as value, 4 divided by 3 gives us negative 28.8 repeated, so that doesn't work. I can go second trace value negative 4/3, and it does not give us one either. 4/3 and negative 4/3 are out. Take a guess. Take one of the other ones. 1/3. So we can grab the calculator, go second trace value, 1 divided by 3. Not quite, but it is 1/2. Second trace value, 1 divided by 2. It is 1/2. So 1/2 is one of our solutions. And we can list it out as a reminder. Inside our cubby would be 1/2. And we can do synthetic division. Because the reason we're doing this in the graphing is to get at least 2. If we can get 2 solutions, we can get it down to a quadratic. And if we have it as a quadratic, we can use the quadratic formula like we did yesterday to solve. Might not always need the quadratic formula, because if it is factorable, we can go from there. Now at this point here, we do our synthetic division. 1/2 times 6 is 3. Negative 11 plus 3 is negative 8. 1/2 times negative 8 is negative 4. Negative 16 plus negative 4 is negative 20. 1/2 times negative 20 is negative 10. 2 plus negative 10 is negative 8. And 1/2 times negative 8 is negative 4, which does give us 0. Okay, 1/2 worked. Now if we look at the chart, well, we only had 2 spots that were positive, yes? And we can see here the other positive one is bigger than any rational 0 we have. So that tells us something. It tells us that none, well, that was already gone, of the other positive values are going to possibly work. They're all out. And we can mark off the positive 1/2 because it's already been removed as a solution. So that just leaves the negatives. Which one do we want to try next? Negative 2/3. Second trace value, negative 2 divided by 3 is 0. So now we can do this again with negative 2/3. We drop the 6. Negative 2/3 times 6 is going to be negative 4. Negative 8 plus negative 4 is negative 12. Negative 2/3 times negative 12 is going to be 8. Negative 20 plus 8 is negative 12, which gives us 8 again, which is 0. Now at this point here, we can continue trying values to find out what the other value of this is, but I have a feeling that our last solution is not going to be a rational, it's going to be an irrational solution. And part of the reason I get that feeling is because of this one solution, the positive one that's bigger than any of the other ones we have. Now we will have another theorem today. Doesn't really add a whole lot, but what it states is if the square root a plus the square root of b is a solution, a minus the square root of b is a solution. If we have one answer with a radical, we have to have a second. They always come in pairs. Just like with our I. If we have one, we have to have the other. They always come in pairs of 2. So there's a good chance the other one is an irrational solution, and it will have to have its pair. So what we're left with is 6x squared minus 12x minus 12. Well, is there a common factor, a number between all three? 6. If there is one, especially a number, get rid of it. Because it's going to make it easier to work if we divide this 6 out. Because it'll leave us with x squared minus 2x minus 2 is equal to 0. Unfortunately, or fortunately, depends on how you look at it, quadratic formula. If what we end up getting is rational, we can do it in the 30xs. If it's not rational, we have to do it part by part. So we can look at that one for this here. Negative b, well, our b value in this case is negative 2. A is the number in front of x squared, so it's 1, and c is negative 2. So we have negative negative 2 plus or minus negative 2 squared, our b squared, minus 4 times a, well, a is 1, times c is negative 2, all over 2 times a. Now this one here will be rational, a rational solution, because we did see that it crossed the x-axis. So we could type this whole thing in. We can't type in the plus or minus because there is no key like that. We would have to pick one or the other. Now I'm going to do it part by part. I will show you how to do it all at once. Our negative negative 2 is going to become positive. The denominator 2 times 1 is 2. Now we can type what's inside the radical first. So it'd be parentheses negative 2 squared minus 4 times 1 times negative 2, which gives us 12. Now if we simplify the square root of 12, we do second square root 12, it's 2 square root of 3. One last step is the 2 and 2 square root of 3. Are both of those divisible by 2? 2 divided by 2 is 2 square root of 3 divided by 2 is just square root of 3, because our 2 divided by 2 is 1. 1 times the square root of 3 is just the square root of 3. Well, that's our other two answers here. So these here would be our 3 or 4 solutions for this here. Now, as you're asking for this here, we could type the whole thing in, but we do need to choose one of our either the plus or the minus first. Or really, you can think of the plus or minus in front of the radical as being there. You just pick plus or minus first. We type the whole thing in, we get this here. Because the only other case is if we select it again, use the arrow, get all the way back. So I can change it to minus, which just gives us minus square root of 3. So we can think of it as 1 plus or minus the square root of 3. So it will give us both. But what's inside the radical has to be positive, a positive number, for this to work. The graphing calculator would do it all at once. It's just going to approximate the square root of 3 and give you a decimal version of the answer. We want it in radical form. Questions on this here? Now really, with most of solving, when we solve these here, the first thing we try to do is graph it and see if we can get as many solutions as we can. For this one here, if we had gotten 4 nice numbers, we'd have been done. But here we didn't get any, so we had to use the rational zeros. Once we did the rational zeros, we found 2 that worked, got it down to a quadratic, and we could solve from there. Questions on this here? Questions on any of these so far? Well, let's look at this next part. The rationals, the irrational conjugate theorem. Let f be a polynomial function with rational coefficients, and let a and b be rational numbers such that the square root of b is irrational. All this is saying is that if a plus the square root of b is a solution, then a minus b has to be a square root, be a solution. Kind of like our complex conjugates, a plus bi, a minus bi. If we have one, we have to have the other. So we won't delve too much with it, but they will do this, especially in the college algebra. They will tell you that given the solve the following polynomial function, given that the square root of 2 is a solution. Well, that also means negative square root of 2 is a solution, so they gave us 2 to start with. Most of the time when they do that, it means either another set of the solutions is complex or irrational. But we're not going to be, well, we can kind of use that, but also we're going to be doing this here. We want to write a polynomial function of least degree that has rational coefficients and a leading coefficient of 1. What they're telling us and what we're doing here is it told us one of the zeros is 3, one of them is 2 plus the square root of 5, and we want to get back to the polynomial function that has these solutions. We're working backwards. So on the previous ones, they gave us a polynomial equation. We found the solutions. Now we're starting with the solutions, and we want to get back to the starting function. Now, according to the irrational root theorem, since 2 plus the square root of 5 is a solution, 2 minus the square root of 5 is a solution. If we have one, we have to have the other. First step in doing this here is to get all 3 of these here equal to 0. So for this first one here, we're going to subtract 3 from both sides. Telling us this one here is x minus 3. The next one, first thing we'll do is subtract 2 from both sides. Telling us that x minus 2 is equal to square root of 5. Well, now we subtract square root of 5. Telling us x minus 2 minus square root of 5 is 0. Well, what's the only difference between that one and the next one? Square root of 5 is, so they should look the exact same, but the square root of 5 should have the opposite sign. Because the first step here would be to subtract 2. Minus x minus 2 is equal to negative square root of 5. And this time we'll have to add the square root of 5 instead of subtracting it, because it has the opposite sign. And we get this here. Questions on how we got to this point here? Next step. Because we just need to multiply these three together. Once we finish multiplying them together, we're done. Whenever you multiply two or more polynomial expressions together, always multiply the complex conjugates or the irrational conjugates together first. These two together first. And the reason we do this is, just like with I, where we figured out or saw that when multiplying complex conjugates together, the I terms cancel out. Same thing's going to be true with this here. So we distribute the x first. X times x would be x squared. X times negative 2 is negative 2x. X times square root of 5 is plus x squared of 5. Negative 2 times x, negative 2x. Negative 2 times negative 2 is plus 4. Negative 2 times square root of 5 is negative 2 square root of 5. And lastly, multiplying through the square root of 5, negative x times square root of 5 is negative x square root of 5. Negative square root of 5 times negative 2 is plus 2 square root of 5. And negative square root of 5 times square root of 5 would be negative square root of 5 squared. Well, the square root and square would cancel. Now, as we look at this massively long set of parentheses, let's combine like terms. X squared, there's only one of them. Negative 2x and negative 2x give us negative 4x. Now, you might be saying there are other x terms, but the x squared of 5 is not the same because of the square root of 5. But positive x squared of 5, negative x squared of 5, they become 0 because they're opposites of each other. Negative 2 square root of 5, positive 2 square root of 5, those are both 0, which leaves us with 4 minus 5, which is negative 1. So all that became x squared minus 4x minus 1. That's why we do those first. Because if there are radicals, any of the radicals are going to cancel out. And lastly, we multiply these two together. X times x squared is x cubed. X times negative 4x is negative 4x squared. And x times negative 1 is negative x. Distribute the 3. 3 times x squared is negative 3x squared. Negative 3 times negative 4 is plus 12x. And negative 3 times negative 1 is plus 3. And when we combine like terms here, x cubed by itself, negative 4x squared minus 3x squared is negative 7x squared. Negative x plus 12x plus 11x plus 3. That's it. So a lot of this is just get it equal to 0 and then multiply. A lot of multiplication. Questions on this problem here? Questions on anything we've done so far today? We good with this here? This is the last one we're going to look at today. Now we have this here. So they told us the zeros are 0, 5, and negative 5 plus 8. So we can set those three equal to x. And since negative 5 plus the square root of 8 is a solution, negative 5 minus the square root of 8 is also a solution. So we have these here. Now, just like with the last one, we do need to get each of these terms equal to 0. Luckily, the first one, x equals 0, is already done. So it's just going to be x. Yeah, no, you had it right first time, minus 5. So our next one is x minus 5. Our third one here, we would. Yeah, we will. Because we can add 5 first. Gives us x plus 5 is equal to the square root of 8. Then we can subtract square root of 8 from both sides, giving us x plus 5 minus square root of 8. Unfortunately, we can't subtract those two because of the radical, because the actual answer for that there is I think it's almost 2.8, 2.9, non-repeating, non-terminating decimal. Otherwise, we could. Negative square root of 8. Add the square root of 8 to both sides. Telling us x plus 5 plus the square root of 8 is equal to 0. Questions on this here before we start multiplying them together? Well, there is nothing that says we have to do just one set of multiplication at a time, because we can do both of these at the same time. So I'm going to do our x times x minus 5. Well, x times x is x squared. X times negative 5 is negative 5x. And well, that's it. And luckily for the first one, there are no like terms. So that's really going to be it for now. The other one, distribute the x. X times x is x squared. X times 5 is plus 5x. X times the square root of 8 is x square root of 8. Now we're going to distribute the 5. 5 times x is plus 5x. 5 times 5 is plus 25. 5 times positive square root of 8 is plus 5 square root of 8. And lastly, we're going to distribute the negative square root of 8. Negative square root of 8 times x is negative x square root of 8. Negative square root of 8 times 5 is negative 5 square root of 8. And negative square root of 8 times the square root of 8 would be the negative square root of 8 squared, and a square root and square would cancel. Now looking at that entire set, well, x squared of 8, negative x squared of 8 will be 0. 5 squared of 8, and negative 5 square root of 8 are gone. And everything else that's left, we can combine with its like terms. X squared, there's no like terms. 5x plus 5x is plus 10x. And 25 minus 8 is plus 17. Yes. The last thing we need to do is distribute these here. We'll distribute the x squared. X squared times x squared is x to the 4th. X squared times 10x is plus 10x cubed. And x squared times 17 is plus 17 x squared. We'll distribute the negative 5x. Negative 5x times x squared is negative 5x cubed. Negative 5x times 10x is negative 50 x squared. And negative 5x times 17 should be negative 85x. Negative 5 times 17, negative 85. And lastly, we'll combine like terms. We'll have x to the 4th, 10x cubed minus 5x cubed is plus 5x cubed. 17x squared minus 50 would be negative 33x squared. And lastly, minus 85x. And that's the answer. X to the 4th plus 5x cubed minus 33x squared minus 85x. X to the 4th. Oh. 5x cubed minus 33x squared plus 5x to the 3rd. 33, 85. Minus 85x. Make it one more time just to make sure. Yep. And the reason I'm doing this is I'm going to go on and graph it. So we see that it does cross in these spots. Yes? Second table, what we were told two of the solutions were 0 and they're still the solutions, yes? So that's one way we can check it. Then the other as well, value. We were told that the other solutions were -5 plus square root of 8. -5 plus second square root 8 is a solution. Trace value -5 minus second square root 8. Yes. So the graphing calculator is a way to make sure we did end up with the correct final statement, and that there wasn't a calculation error somewhere. Now, I originally had y'all doing problems out of the, well, quote-unquote book, the printed version of the book. But I decided not to have y'all do this problem set here. We're going to do this worksheet. Now, problems 1 through 3 list all the possible irrational zeros. You're not trying to solve it. You're not trying to find what values of x make the equation 0. You're just trying to find our rational zeros. So the p over q, plus or minus. I won't be as nitpicky on the plus or minus with these here, but these type of problems like 1 through 3 will show up on the test. And I do count each part, the plus and the minus, as part of your answer. So if you don't put the plus or minus on them, that's half of them gone. So that's half the points lost for that one. So make sure you put the plus and minus. Turn the page. 4, 5, 6, and 7. Number 6, I hand wrote it in, but that should be 224. Just as a, I think most of them are pretty clear. We can see 224. I accidentally, instead of 224, I put 244, which changed the answers completely, and it would have been nigh impossible for us to solve. But these here. Now, all of them you can do. I don't believe a single one of these actually has a radical as part of the answer. Well, one of them does, but you do not have to use the quadratic formula on any of them. Because the one that does have radical answers, we can use the square root method to get the answer. Get x squared by itself, square root both sides. And the last two, 8 and 9, we're doing just like what we did here. I will say number 7 does have all rational answers, and the numbers do look crazy, but graph it, find irrational zeros, or find the zeros that it gives us, and then go from there. Don't even know why I tried that. At home, if you're doing these without a calculator, Desmos graphing calculator, you can do those. You can type them in there. Well, if I can get a keyboard. The shift 6 does the exponent. Shift 6 does the exponent key. But that's it.